Light reaches your eyes every moment of your life, yet for most of human history, no one knew what it truly was. It moves faster than anything else we know, carries energy without weight, and behaves in ways that defy everyday intuition. The deeper scientists looked, the stranger light became. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today we are exploring what light really is, and why its nature continues to reshape how we understand reality itself. Long before equations, ancient civilizations tried to explain light through philosophy and observation. In ancient Greece during the 5th century BCE, thinkers like Empedocles proposed that light streamed outward from the eyes, while Aristotle argued that light was a quality of transparent substances activated by fire or the sun. These ideas dominated Western thought for centuries, even as they failed to explain reflection, refraction, or speed. A turning point arrived in the 11th century in Basra within the Islamic Golden Age. Physicist and mathematician Ibn al-Haytham, known in the West as Al-Hazan, conducted systematic experiments with lenses, mirrors, and dark chambers. In his book of optics, completed around 1021, he demonstrated that light travels from objects to the eye, not the reverse. His work established experimentation as the foundation of optical science and influenced European scholars for generations. By the 17th century, light became central to the rise of modern physics. In 1678, Dutch scientist Christian Huygens proposed that light behaves as a wave, spreading through space as ripples spread across water. He used this model to explain refraction and diffraction, effects that particle ideas struggled to describe. Yet only a few decades later, Isaac Newton offered a competing view. In his 1704 work, Optics, published in London, Newton argued that light consisted of tiny particles, or corpuscles, emitted by luminous objects. His authority and experimental success caused the particle view to dominate science for over a century. Evidence slowly shifted the balance. In 1801, English polymath Thomas Young performed his famous double-slit experiment, showing that light passing through two narrow openings produced an interference pattern. This behavior was unmistakably wave-like. Later, in the 1860s, Scottish physicist James Clerk Maxwell unified electricity, magnetism, and light into a single framework. His equations demonstrated that light is an electromagnetic wave propagating through space at a fixed speed, measured in vacuum at approximately 299,792 kilometers per second. For a time, the mystery seemed solved. Light was a wave, and physics appeared complete. But the 20th century overturned that confidence. In 1900, working in Germany, Max Planck discovered that energy exchange between light and matter occurs in discrete units, later called quanta. This idea was not philosophical speculation, but a mathematical solution to experimental data on black-body radiation that classical physics could not explain. In 1905, Albert Einstein extended this idea while studying the photoelectric effect, an experiment showing that light can eject electrons from metal surfaces only if it exceeds a specific frequency. Wave theory alone failed to explain this. Einstein proposed that light sometimes behaves as individual packets of energy, later named photons. This work earned him the Nobel Prize in 1921 and forced scientists to accept a radical conclusion. Light behaves as both a wave and a particle, depending on how it is observed. This duality was not a flaw in experiments. It was a feature of reality. Repeated experiments throughout the 20th century confirmed it, from Compton's scattering in 1923 to modern single-photon interference tests conducted in laboratories worldwide. Light does not choose one identity. It obeys mathematical rules that transcend classical categories. As quantum mechanics developed, light became inseparable from deeper questions about observation and reality. In the Copenhagen interpretation, formulated in the 1920s by Niels Bohr and Werner Heisenberg, light exists as a probability wave until measured. Only upon interaction does it appear as a particle. This interpretation does not claim that light changes nature magically. It states that physical descriptions depend on measurable outcomes. Later experiments sharpened this mystery. In delayed choice experiments proposed by John Archibald Wheeler in the 1970s and later realized in laboratories, the behavior of light appeared to depend on measurement choices made after it had already traveled through an apparatus. These results did not violate causality, but they challenged classical assumptions about when physical properties become defined. Modern physics goes further still. In quantum electrodynamics, developed in the mid-20th century by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, light is understood as an excitation of a quantum field that permeates all space. Photons are not objects moving through emptiness, but interactions between fields governed by probability amplitudes. This framework predicts experimental results with extraordinary precision, confirmed to more than 10 decimal places. Yet, even this success does not fully answer what light truly is. Is it a thing, a process, or a mathematical relationship? Physics describes how light behaves with unmatched accuracy, but interpretation remains open. Some physicists favor realist views, others informational or relational perspectives. These are philosophical positions grounded in evidence, not mystical claims. Light also shapes our understanding of the universe at the largest scales. In the early 20th century, Edwin Hubble used light from distant galaxies to show that the universe is expanding. Cosmic microwave background radiation, first detected in 1965 by Arno Penzias and Robert Wilson in New Jersey, revealed light released just 380,000 years after the Big Bang. Every photon reaching our instruments carries information across time itself. At the same time, light defines the limits of causality. According to Einstein's theory of relativity, published in 1905 and refined in 1915, nothing with information can travel faster than light in vacuum. This constant links space and time into space-time and sets the structure of reality. Light is not merely within the universe, it shapes the universe's geometry. In practical terms, our civilization depends on these discoveries. Fiber optic communication, lasers, medical imaging, and quantum technologies all rely on precise understanding of light's behavior. Each application rests on decades of verified research, not speculation. Still, unresolved questions remain. How does quantum behavior give rise to classical reality? Why does measurement matter? These questions extend beyond light itself, touching the foundations of physics. Scientists continue to test interpretations through ever more refined experiments, including quantum entanglement studies and tests of locality. Seen as a whole, light resists simple labels. It is neither just a wave nor merely a particle. It is a phenomenon that reveals how nature encodes information, transfers energy, and connects distant regions of space and time. Understanding light teaches a deeper lesson. Reality does not always conform to human intuition. It follows rules that can be measured, tested, and expressed mathematically, even when they challenge common sense. Light shows us that knowledge advances not by choosing comforting answers, but by accepting what evidence demands. This is Mattermosaic, piecing together the universe, one discovery at a time. If exploring how light blurs the line between waves, particles, and reality itself reshaped how you see the world around you, share this journey with someone curious about the deeper structure of nature, and stay with us as we continue tracing the forces that illuminate the fabric of reality.